Let's move on to designing the audio system. Remember that bad sound destroys good visuals. Audience might forgive low resolution, but they will never ever forgive unintelligibility. Every audio design starts with a question. Is it live reinforcement or program playback? Live reinforcement projects voices and instruments to an audience. Program playback reproduces recorded material with fidelity. If you get this wrong, every other decision will collapse. Purpose defines the topology of your audio system. There are three parameters you need to be consistently thinking about: intelligibility, loudness, stability. These three will decide the system's success. When it comes to intelligibility, you need to ask yourself, can the message be understood? For loudness, could it be heard? For stability, can it run without feedback? Every mic, speaker, and processor exists to serve those three. If it's not improving one of these, then it doesn't belong in your design. And when it comes to frequency response and fidelity, not every system needs 20 Hz to 20K. Match frequency range to the use case you have on hand. Speech requires 200 Hz to 6K clarity, for example, not sub-bass extension. Music or cinema needs the full range and more specs. Ignore this and you waste power, space, and cost, of course. Don't forget that every amplifier will add some artifacts, so measure them. Harmonic distortion turns clarity into mud. Aim for a target of lower than 0.5% harmonic distortion for reinforcement. For critical playback, aim below 0.1%. Distortion defines quality more than wattage. And for the sound pressure level required, I want you to remember that loudness is subjective, but SPL is not. So measure in dB SPL with A or C weighting, depending on the function and the environment of the space. A weighting for speech and conferencing, that's the standard. C weighting for high-level environments like concerts or gigs. And try to maintain 25 dB above ambient noise for intelligibility. You can, of course, have more. So measure the reality because it's not about your opinion. And always keep coverage uniformity on top of mind. Uneven coverage is a silent killer. One row too loud or another straining to hear, that's not a good design. Uniformity defines professionalism. Designed to AVIXA A102.01 target. That is plus 3 dB across seating. Achieve with proper loudspeaker placement and aiming. Every seat deserves the same experience. And remember that feedback is physics, not mystery. If mic pickup re-enters the system loop louder than it left, you get oscillation. That is what you hear when it comes to feedback. There are multiple strategies to control this. You can control that through mic placement, gain structure, or equalization. When those three fail, you can use feedback suppression or mix-minus routing. Remember that stability is designed, it's not adjusted. And always identify audio sources. List every origin. Microphones, is it wired, wireless, ambient, instrument, DI boxes maybe. Playback devices, computers, streamers, codecs. Each source defines required preamp count, phantom power, and processing. Take inventory before specification. And as we move forward in our audio design signal flow, your destination will include PA zones, recording feeds, in-ear monitors, and broadcast outputs. Match loudspeaker design to function. Two-way or three-way for full range, constant voltage for distributed paging, and subwoofers for low-frequency energy, and arrays for coverage control. Choose loudspeaker topology for purpose. It's not about symmetry. Don't confuse mixers and amplifiers. Mixers blend and amplifiers drive. Mixers handle mic to line conversion, gain trim, routing, but power amps convert voltage into acoustic energy. Plan for expansion, extra inputs, extra outputs, and phantom power. Future channels are cheaper to design than retrofit. Retrofit is always more expensive. You will undoubtedly encounter signal processors. Those are used to protect intelligibility. DSPs combine equalizers, compressors, limiters, echo cancelers. So use equalization to match loudspeaker response to room. You can use compression to control dynamics and prevent overload. And of course, echo cancellation to clean conferencing audio. DSPs exist to make consistency predictable in audio designs. So how do you spec an amplification system? Amplifier design begins with load impedance. Series wiring adds impedance, parallel wiring divides it. Match amplifier rating to total load or expect distortion and failure. You will be surprised to see this a lot in the field. The formula for parallel loads is the total impedance equals the impedance of one speaker over the number of speakers. For example, 4 8-ohm speakers in parallel equals 2 ohms in total. Power follows math. There are two common types you will encounter in the field: direct coupled and constant voltage systems. Direct coupled gives fidelity and headroom for short runs. Constant voltage, 25V, 70, 100, supports long cable runs and many speakers using transformers. Both have places. Choose based on distance and scale. Select topology for distance. It's not a habit or tradition. Remember that transformers isolate and adapt. Step up increase voltage for distribution and step down converts it back for the loudspeaker. Insertion loss equals wasted heat. So select quality transformers for minimal loss. They effectively trade current for reach. Remember that. And I'm sure some of you are asking, what about cable runs and power loss? Remember to use thicker gauge for longer cables. Excess resistance eats wattage and headroom. Specify gauge per run length and comply with local electrical codes and plenum ratings. Cable gauge is about performance. It's not housekeeping. As you design your audio system, remember that loudspeaker sensitivity defines acoustic output, and learn how to read specifications. When you read 90 dB SPL at 1 watt at 1 meters, you can use the inverse square law that we learned in part 1 to estimate drop-off, meaning every doubling of distance will be a minus 6 dB. Then calculate needed amplifier power to target SPL plus the headroom. So design SPL with equations. Don't eyeball it, don't guess it. Audio design is disciplined translation from electrons to motion. Prioritize intelligibility, balance loudness, and engineer stability. Respect physics and the system will respect you. And remember that perfect visuals mean absolutely nothing if the message can't be heard.